As I said, I'm from Vienna, and I'm working as a software engineer on the Couchbase SDK team. I'm mostly maintaining all of our JVM related things. And when Matthew said he's doing a conference here in London, I was thinking, oh man, I wanna talk here, and I want to submit something really interesting. So I didn't submit those introduction to Couchbase kind of talks, but what I wanted to talk about for a long time is we did a completely new Java SDK, and I think we did it in a really, really nice kind of way. And that's what I'm talking about here. So of course it's very Java heavy, it's very Java heavy related talk, but most of the concepts I'm going to show you are also applicable to other languages as well. So I'm talking about ring buffers, I'm talking about backpressure, I'm talking about API design. So of course I'm going to showcase the Java SDK from Couchbase, but basically you can apply this to all different kinds of projects. So let's first start with why. Why the heck do we even set out to build a completely new SDK? Because we already had one, right? So it's a major undertaking, I would say, to build something completely new. Why didn't we just stick with the old one? To give you a little bit of context, I'm going to tell you a little bit about the history about Couchbase and how we came to the current to the current state and why we had to move to something completely new. So in 2003, there was the memcached project. So who is using memcached or who has heard about it? Yeah, like quite a lot. So in 2003, it was quite important to take load off relational databases. So they built this in-memory data store, key-value base kind of thing, and it worked really well. It still works really well for today. Now, memcached really shines if you just want to stick data in, arbitrary data, and then grab it out by key. Now, it turns out there are a few things missing in memcached. So around in, let me get this one here. So in 2004, going forward, what happened is that more and more people contributed to memcached. Dustin Sellings, Trond Norby, Steve Yen, they actually all work at Couchbase right now. So what happened at that time frame was that people were saying, you know what, memcached is really nice, but I'm missing two things. I'm missing persistence and I'm missing replication. What happens if my node goes down? What happens to my data? So for everyone who's used memcached, you're using it because your main data store is not able to handle the traffic, and if your cache goes down, everything goes to the database and everything will slow down. So out of that effort, Membase, or actually even before that it was called Northscale. So they created a product called Membase at the, I think, 2005, 2006 area. And it actually added persistence and replication to memcached and multi-tenancy, those kind of things. So it was really a persistent replicating cache, but it still had a key value type of access. Now going back to memcached and Membase, it was cache key value oriented. So the SDKs and the APIs at that time, of course, were key value oriented. Now, when they built Membase, the product, of course, they intended to be 100% API compatible with memcached, so you could use it as a drop-in replacement. So this is where I would say our SDK history kind of comes from. A few years later, Membase, they joined forces with another company called Couch1, and eventually they built a product called Couchbase, which is still called today. So Couchbase Server is a document-oriented database. So it not only has key-value type of access, but you can do querying and so forth. And to that regard, the server moved from a persistent replicating cache with key-value type of access to a more document-oriented database. Now, of course, this also means that the programming model from an SDK perspective has to change, because if you're working with a document-oriented database, you can go very far with key-value type access. But as we added features, as you see later, it turned out to be, I would say, very inconsistent, and this is why we were on the lookout for a new SDK. Now, Couchbase kind of focuses on 4 different things, and I don't want to go into all the details, but I want to mention why they're important, because they also reflect on the SDKs, and most of those points here very heavily influence the technologies we had to use underneath to accommodate those. So scalability in Couchbase Server, you can add and remove nodes on the fly. And this is actually not very trivial to do on the SDK side, because as servers can come in and go out all the time, and the SDK needs to be able to handle that. So we don't require you to restart the application server just because you added nodes to the cluster. No, the SDK needs to handle that during serving your traffic. So there needs to be a lot of intelligence underneath to make sure that data is moved around in the correct way and we know to which node to go to, and if we get an error, we want to reschedule and so forth. That's on the same page with always on because we want to make sure that literally you never need to restart the application server. Even if you swap out the whole cluster, the thing needs to keep running, right? Flexibility, so you can store everything because we are still coming from a very key value cache oriented background. So you can store serialized Java objects, you can store any binary data that you want to, but if you store JSON, you can make use of secondary indexing and so forth. Now, this is also a challenge, or this has been a challenge for quite some time because coming from the memcached history, we were treating the value as opaque. Yeah? Like put anything you want in there, and if it happened to be JSON, well, that's fine. Then you can use the secondary indexing on the server side. As it turns out, of course, people started to use checksum and Google JSON on the JVM and other tools in other languages to create those JSON, marshal them, and then send them over the wire. So for the new SDKs, what we also were thinking about is making JSON a first-class citizen on the client side as well as on the server side to give you a much richer experience when working with your data. But still, we have a large set of caching users. So every feature we added, we also want to make sure that if you store any kind of data, it still works perfectly fine the same way. And the last one, and I think this is also very critical, is performance, because we have users running 2 million operations per second on clusters, and you need to make sure that they can sustain such a load on the client side. So you can imagine doing blocking I/O is probably not the best thing when you are in that kind of period. So we're using Netty, NIO underneath to accommodate those kind of performance characteristics, which I'll talk about in a minute later. So we support a whole range of SDKs. So we support Java, .NET, PHP, Java, and so forth. The main point to take away here for you is that PHP, Ruby, Python, Node.js, they're all built around our C library, which is called libcouchbase, which covers all the nitty-gritty details like configuration management and so forth. This is handled here, and the other languages are just bindings on top of the C library. Both Java and .NET are complete standalone projects. They do not depend on libcouchbase. So they need to re-implement everything under the covers as well. Now, focusing on the Java SDK and looking especially at the I'm always calling it the old Java SDK, but the 2.0 SDK has only been out for a few weeks. So this is what 99% of our users running in production right now, or even 100% probably, is that the old SDK, it extended SPY memcached. So SPY memcached was one of the first memcached clients available on the JVM. Actually, one of the people contributing to memcached, Dustin Stellings, he wrote SPY memcached back in 2003 and 4 and so forth. So when you're using it, of course, because it's like here for around over 10 years, it has some legacy into it, and we had to deal with it on a regular basis. Even when we added capabilities like configuration management and views, we had to deal with a little bit of maturity, like with all older projects. So this was one of the things we had to rework for the new one to give you a better experience. And of course, it's stable and mature, because software that has been around for so long, not all of the bugs, but most of the bugs have been ironed out, and it was trusted and mature. And actually, SPY memcached is used by a lot of other libraries out there as well. So we are maintaining it, but you can use it right away without any couchbase kind of thing. So you can still use it with memcached. The whole thing is an older code base, of course, and it got difficult to maintain and evolve over time. Especially, we are now adding different query capabilities, and then we thought about how can we add those to the old SDK, and it got clearer and clearer that if we want to do it the right way, and we don't want to take more and more time to cram those features into the old one, we probably need to think about rewriting the whole thing. And also, there were some API consistencies over time, and I can tell you about those in detail, but just to give you a rough idea, so this is the memcached client interface. And you can see there is a set operation to store data on the server side, and it's asynchronous. It returns your future of type Boolean, so it's a completely asynchronous API. But if we want to load a document, the get method, it's synchronous, and it gives you the value back. If you want to go for the asynchronous variation, you use async get. So you can see it's inconsistent, and there are some non-obvious things if you use the API. So we took the chance to clean that up as well as part of our efforts. Now, I'm going to talk about two different things now. there were two orthogonal concerns we had when we were dealing with a new SDK. The first one was how we are reworking the API, the user-facing thing. And the other part was how we are reworking the SDK architecturally. So I'm first going to talk about the API, and then we are going to tackle architecture. So API-wise, Stefan, 2 talks before, he talked about Reactor, and he said all of the hipsters are now using RxJava. Well, apparently we are one of the hipsters, even if I didn't know about that like until 2 hours ago, but that's probably fine. So we thought, all right, so we were using asynchronous APIs all the time. But what I saw looking at a lot of users' code is that if you're using asynchronous APIs, you still have a lot of challenges, especially if you're, I mean, we added listeners, but futures itself, they're very hard to deal with, especially if you want to compose stuff, like loading 2 different documents and then doing something asynchronously as well. So composing asynchronous operations is very hard. Even if you use listeners, you very quickly get into callback hell. So when very early, I think over 1 year now, I was evaluating different alternatives we could use inside the core to make it very resilient and scalable. And there were some libraries out there. There was Reactor in the 1.0 version, and then there was RxJava. And eventually we picked RxJava for some reasons. The main 2 reasons were most people were using RxJava, so the community was larger. And the second one is that it doesn't ship with any dependencies. So Reactor has some dependencies, which is fine if you use it in an application server. If you are shipping an SDK, as we do, the more dependencies you add, the more likely you're running into conflicts. And this is something we were bitten a few times before, so I wanted to keep the dependencies as low as possible. And also it's very mature and feature-rich. Netflix is using this in production for, I think, 2 years now, around that period. So it's a very great project. So I said, you know what, let's use this in the client itself. But then when I used it more and more, I thought, that's actually really quite powerful. Why not expose it to the user right away so people can build their application stacks on top of our SDK the same way we build the SDK underneath, because it's very, very efficient and feature-rich, and it allows you to express so much things so nicely. So eventually we said, you know what, let's expose a Reactive API right to the user. Now, for those who don't know Rx, if you're working with Rx observables, you can think about it that way. So in Java or any other language for that regard, if you have a synchronous access to a single value that you want to get out of, let's say, an interface, you're returning type T. I mean, that's obvious, right? If we are doing it asynchronously, what we are normally using in an interface description is a future. And the future tells us once the data is ready, and it's not saying an error happened, eventually you'll get the T and you can take it out of my future. Now, what the future essentially does, it's expressing a side effect, and side effect is latency. So if you are building APIs which are under the cover asynchronous, and you have to block all the time, and you're exposing it like this, what you are not only doing is you're not slowing your clients down, but you're also losing very important semantics like a future, which tells you right away, hey, I have a side effect, and side effect is network latency for an SDK, right? Now, if you're looking at, we want to get multiple data, multiple, I would say, let's say events or something out of a system, we can use an iterable. And the iterable is pull-based. So you get an iterator for, like I say, a collection, and you're ready, if you're ready to take out some data, you're asking the iterator, hey, do you have new data? And if yes, you can grab it and do something with it. Now, the asynchronous cousin to the iterable is the observable. The only difference to the iterable for now, for you, is that the observable is push-based. So instead of you asking the iterator, hey, do you have new data? What the observable does is it notifies the subscriber, hey, I have new data for you. So if you do a GET request and you're fetching a document from the SDK and you're subscribing to the observable, what will happen is the SDK will notify you once the data is ready to be loaded. And then you can apply your transformations and do all the nice things if you want. So looking at iterable and its cousin observable in a little more detail. So if you want to grab data out on an iterator, you're calling next, and you grab the data out of the iterator. In an observable, you're only dealing with events. So every time data comes along, the onNext method is called on your event handler, and then you can do something with the data. If an error happens during your observable sequence, in an iterator, because it's synchronous code, an exception is thrown. We cannot throw an exception in an asynchronous computations, so there is an error handler, and your error handler will be called with the throwable, and then you can do whatever you want with it. We'll see some error handling strategies a little later. So this is just to give you a broad overview of the concepts. And finally, if your iterator doesn't contain any more data, it's done. It will just return your call in a synchronous environment. And in an asynchronous one, the onComplete method is called. When you're implementing a subscriber, you can choose to subscribe to any of those events, just one of them. That's completely up to you and what you want to do with it. But you have all the functionality available. Now, if you want to work with observables, and I'm giving you a really quick rundown of how to work with observables. Of course, we have all this in the documentation. There are a lot of talks online about RxJava. But for those who have never seen it before, I want to give you a rough idea of how it is to work with. So the first thing we want to do is we want to create an observable so we can consume it. So there is a method called just, and this is a marble diagram. So at the top, you see input data, and then something happens with your data, and in the end here, something pops out of our function. Now, the line here is our observable stream, and every time you see a ball here, it's an item emitted, and then with the bar here, it means the observable is completed. If you see an X, it means the observable has failed. So this is a very simple but very powerful notation. If you look at RxJava documentation, all of the operators, and there are quite a few, they're all documented like this, which makes it very easy to grasp what's going on in this operator. So here we have a list of items, and when we call just on the observable, all of this will be immediately emitted into observable stream, and we can subscribe to it and do something. So that looks like this. So we have an observable which emits A, B, and C, and then we can subscribe, and we print it out. So what we get is got A, got B, got C. So that's very simple, but it shows you how to create an observable and how to subscribe to the results and do something with it. Now, I mean, that's not very powerful, right? What we can also do is we can transform, so we can apply a function to our data which transforms it from one type into another type. So we can use something like map to transform it from circles into diamonds. So our map function applies to every element and then emits it to another observable, and this is important. Every result of this function here is another observable, which means we actually got two observables. So you could imagine you could have the source observable stream here and have two different map functions, and in the end you get two different streams depending on what you want to do with your data. So here we have observable from. We create a list, and this is groovy code, and then we can use map function to multiply our data. So we pass in 1, 2, 3, 4, and 5, and the subscriber never gets to see 1, 2, 3, 4, and 5, but it actually gets to see the result of our computation. So 1, 4, 9, it multiplies with itself, of course. So 1, 4, 9, 16, 25, and finally, we have an uncompleted event which says sequence complete. So this is a map function, very simple, but also very powerful, because it also allows you to extract data. For example, if you use it with the Java SDK and you fetch a document, you get a JSON document, but sometimes you only want a subset of the document. So you can use map to map from, let's say, a JSON document to string. And the subscriber down the path doesn't even have to know it came from your database. It only knows, you know what, I'm getting an observable sequence with a string, and eventually I will be notified once my data is ready. This is a very expressive way to build APIs. And then there is flatmap. Flatmap is maybe a little harder to understand, and it takes some time to grasp the concept, but you can think of it as a map function. But inside your map function, you are sending off another asynchronous request. So what it does is, so here we have our source sequence, which emits 3 items. And then we flat map from type T to observable type X. So we are mapping from asynchronous, basically from a specific item into another observable sequence. Now, that wouldn't be very nice to handle, because if we would just have used map, we would have, the next type would be observable of T, which isn't very nice to handle. So what flatmap does is it flattens the observable into the other one. So even if we send off an asynchronous request inside our map function, the resulting subscriber has no idea that we actually did 2 different asynchronous calls, because we are still ending up with one observable sequence. That's actually quite powerful, because for example, in the Java SDK, we have a get method, which allows you to load the document from the master. But we can apply an error method, an error handler, which says, if an error happened during this call, go to the replica nodes and fetch all the eventually consistent data from the replica nodes. So we can compose that in an asynchronous function, and then the subscriber, even if we expose it in an interface, doesn't even have to know that it's actually 2 asynchronous calls that went out on the wire. It just gets notified once the result is available. So it's getting much clearer if we see an actual code example a little later. And then there are also a multitude of other operators you can apply. I'm just mentioning a few here. So I'm showing you filter right now. So filter allows you to give it a predicate. And every time if the predicate is true, it will allow to pass the item afterwards. So giving it subscribing, giving it to the next subscriber. And if the predicate is false, it will just remove it from your sequence. Now, here's an example. And this is using the Couchbase Java SDK as well as Java 8 code. So I'm giving you a quick rundown. So we are calling the query method on our database bucket, on our data source. And we're doing a query. We say, give me all beers by name, but limit it to 100 items. So this is like a regular query. And what we will get back is 0 to 100, depending on how many items match our query, rows. So we get a result which contains rows. Now we're using flat map to map from our result to each individual row, because what you get back from the API is a result, which has an observable method called rows on its API to then stream all the rows, because you can imagine we are returning your result right away once we get the response from the server. But because you can get thousands and thousands of rows from your query, of course we don't want to queue them up. We want to stream them to you as they get available from the server. So we are telling you, so we are telling the client, the code, we don't care about the result. Just notify me once every row is available. Okay. The next flat map says, I don't care about the row. I want the full document, because you can imagine most of the time when you do an index, you don't want to put the full document into the index because it just wastes space. But we always give you the ID to the document, so you can say on demand, I want to load the full document. Okay? Don't worry as much about the semantics if you haven't used Couchbase before. But finally, we got the full document, and then we're using filter because we don't care about the full document. What we care about is every beer has an alcohol by volume in its document. So we are grabbing out the alcohol by volume, and then the next method here is a count method. And the count method has no idea that we did network calls before, right? Only it does it counts all the items that get emitted to it. So all beers which are lower than 5% alcohol by volume will never make it to the count method. And now here comes the really important part, which is very hard to get right with synchronous programming. We are applying a timeout of 10 seconds to this complete sequence. And even if it's not obvious right away, this means we are touching the server one time here, and then we are streaming hundreds of rows from the network, and then we are doing one binary get call for each document ID we get, so another potentially 100 requests to the server, and then we filter for each and then we count, which means that we are easily touching potentially the server here 100 times, and then we stream full HTTP, so let's say 105 times we're touching the server. And we can apply an overall timer to the complete sequence. And if you're dealing with synchronous code, most of the time you apply the timer right away to each call. But it gets very hard if you want to have a full asynchronous sequence and you want to apply a full timer to it. I didn't even show you error handling right now, but if you want to do error handling for those kind of scenarios in synchronous and callback code, it's very, very hard, trust me. And then finally we subscribe to the whole thing and just print out the result, which will probably print out 54 or something, I don't know how many beers of those hundreds we fetch have an alcohol by volume over 50, okay? Error handling. There are many methods available. One of them is on error return. So if something fails in our sequence, we can have a fallback. So just a single value as a fallback, saying if something fails, just return this one. That's fine. But then there is also on error resume next, which allows us to do, if something fails, we can resume with another observable, right? Another asynchronous request, which gets flat mapped onto our actual stream. So this subscriber here has no idea that something went wrong up here because we told it transparently, oh, go over there and do something like this instead. Now, maybe that's a little abstract, but here's a real-world example. So we are fetching a document from the server side. It documented this beer, so we are fetching it. If we fetch it, everything is fine, all right, we move on. But if something fails, let's say we are fetching the document from this node, and right at the moment someone pulls the power cable, the node is down, and we cannot fetch the document. We will get an error back. Our observable will fail. So what we can do transparently is we can say on error resume next, and then we call the get from replica method on our bucket and tell it, let's say we have 3 replicas configured on our Couchbase server cluster. We can say, if this initial call failed, fall back and fan out to all of the replicas available and give me your data. So I don't want to end up with no data. I'm fine with just some data. And what we can do is we can call first, which gives us the first result, and then we move down. So we do the map call, we apply the timeout, and then finally we can even do more error handling. We can say even the full thing failed, print return not found, right? So we can, for different kinds of errors, we can have very, very good error handling. So here is an example of our Couchbase API if you want to connect, and this is a synchronous one. And this is one thing we learned is that we started with an asynchronous API, but we very quickly found that it was very hard to teach people RxJava and the new API at the same time. So right before GA, we added a synchronous wrapper around the asynchronous API. So you can start with the synchronous one, but you can always tap into the asynchronous flows if you have the need for it. So you can mix and match depending on your needs, and you get the best of both worlds. So we're connecting to the cluster, we're opening the bucket, and then we can use it. If you want to get access to the asynchronous bucket, which has all the observable APIs, you just call async, and then you get access to it, and then you can use it. Or you can just go to the asynchronous one right away. Of course, this is all in the documentation, and you can look that up. One thing we learned is that you need a consistent API. So you can see this is the asynchronous one. We have observable JSON document get, observable JSON document get from replica. So we took the chance to clean up all the API. It exposes a very consistent API, not only across the Java SDK, but also across all of our new 2.0 SDKs. So if you look for get from replica on the .NET SDK, you will find it as well, right? Another thing we learned is document the right way. Especially with observable sequence, it's probably not, you probably won't see it right away how your observable can fail. So for example, here's the Java doc. We say the returned observable can error under the following conditions. And then we explicitly define under which condition which error is raised, so you can very easily build your own code to reflect those scenarios. You can opt and say, I don't care, I just catch everything. But most of the time, you want to apply different error handling characteristics for different failures. Imagine you're overloading the server, it doesn't make sense to retry immediately. You want it to back off, something like that. So it enables you with this knowledge. Also, we did a wrapper around the asynchronous one for the synchronous API. We were thinking about, maybe we should put it into one interface, but we ended up not doing it because it gets very messy. You don't know, is it an asynchronous one, asynchronous call, synchronous call? So what we ended up with providing a wrapper, and there you can see how a synchronous wrapper looks like. We're using the asynchronous get call on the synchronous one, and then we call the timeout, which you can pass in, or we have a default one. And then we block on it, so you can always block an observable and turn it from an asynchronous one into a synchronous one. So this is the nice thing about observables. If you love iterables and you want to work with synchronous code, you can always go from the more advanced way to work with data to the less advanced one. So lessons learned from this one, it's a huge benefit, and we had very good feedback from users using those reactive APIs. Make it consistent, but also document the scenarios, how your observables can fail. This is very important. And expect the learning curve. It's not trivial to get started on this new concept, but providing a synchronous API and then letting people pick out specific scenarios and use the asynchronous one really, really helps. Now quickly, because I know we're running a little bit out of time, I want to talk about the new architecture of the SDK. So what we decided was we wanted to split up the JVM SDK into 2 parts. We have a core module, which we call core.io, and then we are putting language bindings on top, which means that we can put all the nitty-gritty details into the core package. And then we have a Java client, we can have a Scala client, Groovy one, JRuby one, and so forth, where we can provide first-class experience for all of those languages, but we don't have to implement everything over and over again. Now, this is how the core.io module looks like, and I only want to focus on one thing. If data gets passed into this core module, it lands in the ring buffer. And the ring buffer is a very powerful thing. So we also use the LMAX Disruptor here because it's one of the fastest ring buffers readily available. And it allows us to do 2 things. The first one is called smart batching. So imagine you have your producers, and our producers, so your application threads, would talk directly to our I/O threads. You would get a lot of contention. But by putting a ring buffer in between, what we can do is the user threads actually talk to the ring buffer, put your requests into the ring buffer, and then on the other side, we are taking it off the batching thread, right? And then if our I/O is slower than the users, we can mitigate that effect by taking more data at the same time and putting it onto the wire. We also apply backpressure, which means that if you overload the system completely, we will fail your observables right away saying, oops, you're completely filling up our system, but without getting the whole thing swamped by accepting more and more requests, we are failing fast, and then it's up to you to decide, okay, I want to back off as well to my, let's say, my HTTP API, or I want to implement more sophisticated retry logic. We are using Netty under the covers for very high performance I/O. If you're interested in that, talk to me later. I have a lot of war stories to share about Netty. I think it's by far the absolutely best NIO library you can find right away. So this is from a synthetic benchmark I did with Netty, talking to Couchbase server. You can see 800,000 of operations per second going over one application server to Couchbase. Okay, so there is a lot of things we are doing inside to give you very good batching effects, mitigating system calls and so forth. And what's the nice thing about Netty is that it allows you to put your data, I would say, encode and decode very straightforward. You don't have to deal with the nitty-gritty I/O details right away. The only thing you're doing is you're initializing the whole thing, probably enabling SSL. So this is real code from our SDK. If you want to enable SSL on the configuration, whoop, let's plug in an SSL handler. Or you want to, on the logger, trace is enabled. Whoops, let's add a logging handler, which trace logs every single byte that goes on the wire. If not, they are not added to the pipeline, and they don't share any resources or don't waste any resources. And then finally, we apply different handlers depending on those endpoints. So we use key-value type of access, different handlers. We use, for secondary indexing, we use different handlers. So using Netty for UI projects is very easy and gets you from 0 to awesome performance and really maintainable code right away. So last slide for today, lessons learned. We found that we really want to build for the JVM, not for Java, with this core package. We have someone working on JRuby right now. We have Scala in the works, so we can provide first-class experience for users out there for other languages. Start benchmarking from the beginning. It's something that I found very valuable. And using a ring buffer and batching the requests as they come in really allows you to amortize slow I/O, and you can take more of the ring buffer at the same time, put it on the wire, and therefore get some bad effects. Use backpressure. Do not let your systems to be swamped. Fail fast to the upper layer so they can decide what they want to do next. Use Netty for I/O and be happy. So I really think that's accurate. And bundle your dependencies. So this is my last, I would say my last advice to you. If you're building libraries that you ship to other people, make sure to repackage them and ship the dependencies inside, because the more dependencies you expose to your users, the more trouble you run into. All right then, thanks very much, and if you have questions, talk to me later.